28 minutes to 10 o'clock. You are listening to the morning review. It is that time of the week where we speak to Dr. Chris Smith, the naked scientist. Good morning, sir. How are you doing?
Yeah, I'm very good. How are you?
I'm very good, thank you. I have a bit of a block nose, but I think it's because of all the cold weather that we're having here in Cape Town at the moment. So I'll start with this. It's a message from Claudia in Hermanus, and Claudia asks, if I can just get it up, why does a gas heater heat up a room faster than an electric heater? That's the message from Claudia.
Morning, Claudia. Well, the bottom line is that energy, heat, is heat, and it doesn't matter where it's come from, it is heat. And what makes a difference to the temperature of the room is the average amount of energy in the molecules, the average heat of the room. And the room has a certain volume, and the molecules in that room have a certain amount of energy. To push the temperature up, you've got to give them more energy. So the faster you can push energy into the room from a heat source, the faster it's going to warm up. You can't argue with that. It's physics, and it doesn't matter where the energy comes from, the temperature will rise. Now, if you've got something which is producing heat at a certain rate and it's doing that at the same rate as a gas heater, then they're going to warm the room up at an identical rate. What might differ, though, is the way in which one convects the heat out into the room, so some parts of the room might heat up a bit faster. If you've got a radiative heat source, it's going to feel warmer in some positions than if you've got something which is just producing a lot of hot gas. So it will probably be a subjective difference when you think it's warmer from one source than another, but if they're both producing energy at the same rate, then they're adding energy to the room at the same rate, and therefore the ultimate temperature of the room is going to be the same. But I think it comes down to how they actually get the energy into the room and how they distribute it and how they distribute the air currents that affects how quickly you reach that average temperature. So you'll get hot spots with some heat sources than others, and that may be what's being referred to here.
We're taking your calls to the Naked Scientist. Denise in Tableview. Good morning. How are you?
Good morning, Lisa. I'm fine, just freezing cold. I would like to ask Dr. Chris a question. Dr. Chris, could you tell me what the difference between Alzheimer's disease and dementia is?
Yes, morning. And obviously we've got the opposite problem at the moment because we're having crucifyingly hot temperatures and we're having heat warnings issued here with sustained temperatures hitting, well over 30 degrees, which is extremely high for the UK in some parts of the country. So we'll trade you a bit of your cold for some of our hot. How about that? In terms of these words, they are confusing, a lot of these terminologies, which refer to broadly the same thing, because we've heard about senile dementia, we've heard about Alzheimer's disease, we've heard about brain atrophy. All these sorts of terms get bandied about. They're all unified or united under the common outcome that there is a problem which leads to loss of brain volume and loss of brain function. But the process by which that is arrived at can be different. So although you end up with a dementing illness, which leads to a loss of brain function because of loss of brain volume, loss of brain cells, the route you get there can be different. And that's why there are different names for some of these different conditions. Alzheimer's disease refers to a very specific type of dementing illness, and this is caused by the accumulation, initially very slowly but faster as we age, of a protein which is called beta amyloid. And this builds up in the brain and causes these plaques or aggregates of this material in the brain. That's the hallmark. If you look in the brain tissue, you find these blobs of this abnormal material in there. We don't know if they're a symptom of Alzheimer's disease or if they actually cause Alzheimer's disease. They do appear to be toxic to nerve cells, but they may actually crop up because nerve cells are being killed by other processes and they're being made. We don't know for sure, but that's one type of dementia. You could also have a series of small strokes, and another kind of dementia is called multi-infarct dementia. This is where a person over many years develops a sequence of small strokes which slowly prune away bits of brain tissue, leading to overall a loss of the volume of the brain and a loss of critical functions. And over time, the person's cognitive function can drop away. And it's often that you'll get a mixture of these things. So a person may have a degree of atrophy caused by Alzheimer's disease, and they might have a stroke on top. There may be other factors like drugs and alcohol. People who use a lot of alcohol are damaging their brains. HIV, if you don't control HIV with drugs, and you get AIDS, you can get AIDS dementia. And this is where the proteins that are produced by the virus can directly damage nerve cells and lead to their loss in the brain. So there's a range of different pathways to get to an ultimate common outcome, which is a loss of cognitive function. But I agree, the words are quite confusing.
So it's a case of, and forgive me if I'm stating it incorrectly. So all Alzheimer is a form of dementia, but dementia is not necessarily a form of Alzheimer's.
That's right. So dementia is the effective functional outcome of a person whose brain doesn't work as well as it used to and appears to be getting worse. Alzheimer's, named after Alois Alzheimer, the scientist who described it, is one form of dementia. There are many others. Parkinson's disease, which causes muscle tremors, rigidity, difficulty in initiating movements, also has, in the latter phases of the disease, a degree of dementia to go with it. Huntington's disease, another movement disorder but which has cognitive functions affected as well, is another form of dementia. So it's a word that describes loss of brain function over time.
Plenty of questions now coming in of how do we offset or delay the onset of Alzheimer's or dementia. This question asks, please explain the use of magic mushrooms, I guess, and other psychedelics by the Mayo Clinic in the US in treating Alzheimer's and dementia. I know that microdosing has also been suggested as a way to treat some form of mental illness as well.
People are using some of these agents, including psilocybin, which is what's in magic mushrooms, and LSD, which is lysergic acid diethylamide. Hoffman invented that, didn't he? And then had that fabulous bike ride home where colours and things became very strange and he realised what he'd stumbled upon by accident. But a lot of these chemicals are being explored as possible therapeutics for a range of different indications. I'm not aware that people are finding that they're effective against dementias, but there's actually quite a lot of active research now into depression. And this is bearing a lot of fruit. And the reason that scientists think that this can work is that we've spent quite a bit of time now studying how these psychedelic drugs affect the brain and the rigidity of our learning. And so what it can do is loosen for a short while the things that we regard as fixed learning in our brain. And so if a person's become chronically depressed, if you give them certain psychedelic agents, then actually they can unlearn their depression and they re-evaluate their mood and they can learn better strategies to become not depressed.
Heather's asking, could you ask Dr. Chris, is growing up with parents using aluminium pots also, could that also result in dementia? Also, people asking, do you know if smoking causes dementia?
The smoking answer is easy. It definitely does cause dementia. Smoking is probably the worst thing you can do for your health on many, many levels. And the best thing you can do if you do smoke and you choose to is to give up, because it has the biggest impact on your overall health profile and your likelihood of living another 10 years than anything else you can possibly do short of not throwing yourself off a building or something. It's really very valuable if you can cut down at the very least or give up at best smoking, because smoking damages every tissue in your body and it's particularly bad for blood vessels. And people who smoke, when we put them in the brain scanner, we can see a very characteristic set of changes in the small vessels in the brain, the small blood vessels that nourish nerve cells, and they look quite different in people who've smoked a lot compared with people who have never smoked or have given up. And you get this very characteristic flared picture on the brain scan, and it's because of small vessel disease. And this is because you're effectively damaging the vessels. You then starve neurons of essential nutrients, including oxygen, and that causes ultimately their loss and destruction. So smoking, very good idea. Now, the aluminium, not smoking and giving up, very good idea. Now, the aluminium story is more complicated, and this is very what we call confounded, because there are lots of things that go together which are all mixed up in the equation, and it's very hard to see a discrete signal. There are some claims when people have looked in the brain tissue of people with Alzheimer's disease and they have seen those plaques, those aggregates of protein, beta amyloid. If you look in the core of those, you can sometimes find aluminium. And this has led people to speculate that perhaps aluminium caused them to happen in the first place. On the other hand, if you've got an abnormal blob of protein in your brain, it's perfectly possible that that could act like a sieve and trap some aluminium that was just passing through and lead to the aluminium building up there because that's an abnormal protein. So we don't know whether the abnormal protein catches the aluminium and the aluminium's there as a bystander, or whether the aluminium helped the abnormal proteins to begin to build up in the first place. There's some evidence that people who are exposed to a lot of aluminium, for example from cooking pots and so on, might go on to develop dementing illnesses. On the other hand, there are many other factors that, as well as using aluminium cooking pots, that those people are exposed to that could well be accounting for the dementia, and the aluminium has got nothing to do with it. So at the moment we don't have a clear picture. The current guidance is if you do use aluminium cookware, it's perfectly safe, but don't put very acidic things in it like rhubarb. Don't make rhubarb crumble. Rhubarb is one of the most acidic plant things that we cook. If you make your rhubarb crumble, don't make it in an aluminium pot, because it will liberate lots of aluminium metal and put that in your food. And if there is therefore a risk, you will be increasing your dose. So don't do that, but otherwise you're probably absolutely fine.
Janus in Fishhook, how are you doing this morning?
Hi, good morning, Lester. Good morning, Chris.
Morning.
Nice to hear your voice again. A lot of information. My question is, what do we know about our planet Earth? At schools, we were told that our planet consists of layers. They say that during the beginning of our Earth, there was a collision between us and other planets. Maybe humans being also wasn't, as Darwin said to us, we came only from the gorillas and the chimpanzees, because at the moment we don't see this monkeys talking to each other on the cell phone or playing the games, computer games, and we do this. So I think this is more complication, more questions.
Thank you so much, Janus.
Quite a lot of questions rolled into that one. What we understand about the Earth is largely informed by not having gone there, of course, because the Earth, the radius of our Earth, is about 6,000 kilometres. So you'd have to dig a hole 6,000 kilometres deep to get to the very centre of the planet. But what we can do is to use natural phenomena, earthquakes, to effectively investigate the interior of our planet. And a very clever scientist who was a Croatian scientist about 100 years ago called Mohorovčić, who was in Zagreb, actually did these amazing calculations. I've seen his notebooks where he was working to, in some cases, 10 decimal places, measuring the time at which different waves produced by earthquakes starting in one place arrived in different places at different detectors on the Earth's surface at different times. And he was able to use these waves going through the Earth to work out that there must be different layers inside the Earth, because where you have one type of material and then a boundary into another type of material, you get reflections or refraction of these waves along the boundary. So the waves travelling through the Earth will travel different distances, and if you make your measurements accurately enough, you can actually dissect apart these different waves travelling through the Earth and work out very precisely, as it turned out, he was spot on, where these different layers are. And so we've obviously refined this in the 100 years plus since, but we now have a particularly accurate view of what's inside our planet, with crust on the top, continental crust where we live, such as the African continent. There's sea floor and oceanic crust, and then under that's a big squidgy layer called the mantle, which is a sort of semi-fluid with the crust floating on top of it, and then the mantle goes right down to an outer core and then an inner core, and the core is iron. Some of it is solidified and made solid iron, some of it is molten and is moving. And because the planet's spinning, the core is spinning, and the spinning of the core gives us our magnetic field. So it's all down to us being able to investigate the travelling of waves through the Earth to get insights into what the planet's made of, together with measurements of how much the planet's mass is. Yes, we know the mass of the Earth. It's about 6 times 10 to the 21 tonnes, pretty big. And we can work out based on that what the density of the planet is, and that tells us what it's made of. Together with also analysis of material like magma coming up, we can analyse that, and it gives us a good idea of the chemical composition of our planet. So we have a pretty good idea what's in there. The other question that was alluded to is this potential collision with other planets, and that's absolutely true. About 4.57 billion years ago, we didn't have a moon, and then abruptly we did. And the reason we did is because when the solar system was first forming 4 to 5 billion years ago, a couple of planets, the Earth being one of them, and another one about the size of Mars, so a bit smaller, ended up on a collision course. And the two smacked into each other. The core, largely, of that other planet that was coming in, we call it notionally Theia, sank into the Earth and joined the core of our Earth. But a lot of the crust material of the two planets was ejected up into orbit around this new blob of material that then coalesced to make the Earth. And that blob of material that was around the Earth, a shroud as it were, slowly coalesced to make the Moon. And that is, we think, why, relative to the size of our planet, we have such a massive Moon, because the Moon is very big in comparison with the Earth. So we understand now quite well what our planet looks like, how big it is. In fact, the ancient Greeks worked out how big it was and how far it was from the sun, and they were pretty close, actually. The calculations they did were extraordinarily good. We know what it's made of, and we think, where the Moon came from. Where we came from, slightly different story, slightly less clear, because obviously there are always gaps in the evolutionary history, but we do have a pretty good idea that we last shared an ancestor with a gorilla about 6 million years ago, a chimpanzee about 4 million years ago, and since then those sorts of animals have diversified along their line of evolution. We've come along ours, and here we are today.
Hilary in Sea Point, I see you, but first, Jerome in Deep River. Good morning, Jerome.
Hi, Dr. Chris. A quick question. With regards to your health and longevity of health, specifically regarding Alzheimer's and cancer, we use microwaves quite a bit. I mean, everybody uses microwave. Does that have an impact on your health and specifically cancer?
As far as we know, no, it doesn't. And the reason for this is that microwaves, such as the microwaves coming out of your mobile phone, the microwaves coming out of your Wi-Fi router, the microwaves coming out of your microwave oven, not that many do escape from your oven because it's shielded, those are about 2.5 gigahertz, 2.45 gigahertz. And if we work out what the energy of a wave like that is, it's judged to be insufficient to damage the bonds between atoms, in other words, break bonds and therefore rearrange molecules. And that's what ionizing radiation, like ultraviolet or X-rays or gamma rays, can do. And it's those sorts of radiations which are sufficiently energetic to damage the chemistry, particularly of your genetic material, your DNA, which is thought to be a risk factor for things like cancer. But microwaves are judged to be much safer because we don't think they're energetic enough to cause those sorts of rearrangements of molecules in that way. And people are doing the experiment all the time, of course. We're monitoring the health of the population in line with the exposure to these sorts of things and following up. And what you should see, if one thing causes a problem by its exposure, is there should be, as we were told by Bradford Hill, a dose-dependent relationship. So the more of something there is, the more of the thing it causes should happen. And we haven't seen such a relationship as things like microwave ovens, as things like mobile phones, as things like Wi-Fi in the home have been introduced. We haven't seen that dose-dependent relationship in any particular disease outcome, reassuring us that the judgment that they're safe is a reasonable one.
Hilary in Sea Point, thank you so much for your patience. Good morning.
Good morning, and good morning to Dr. Chris. Dr. Chris, I have a question about aluminium foil, which we use a lot in our homes, for heating up leftovers and things like that. Is it safe to use with food?
Hilary, as far as we know, yes, aluminium is a very useful, very reasonable material to use in the kitchen, and that's why it's so universal. The only caveat I offered was that there has been shown to be greater amounts of aluminium liberated from cookware when you put very acidic things in it. Because it's a metal, it does react, even though it's protected by a layer of oxide film on the metal surface. If you put something very acidic in it, like rhubarb is the classic one, it can liberate some more metal from the metal surface into the food, and that might carry some kind of health impact. So the best thing to do is to use it with impunity. Aluminium foil is absolutely fine, but don't put your rhubarb crumble in it.
Taking your calls. We have 5 minutes left with the Naked Scientist, Dr. Chris Smith. But let me go to some of the messages on our WhatsApp line, seeing that it is the Olympics. Chris, the question is there a limit to how fast a human can run or a human can throw if they are not using performance-enhancing substances? As in, is there a physical, mechanical limit to how fast the human body can run?
Well, of course, we have seen over the years with each successive Olympics and Commonwealth Games and other events, we've seen a progressive improvement in performance, and we've seen more and more records being broken. Not all, but many. Now, there's a range of factors here. Some are that the materials that people are using, the tracks that they're running on, and the conditions they're running in have been ideal under certain circumstances and improved. People are using much better equipment now. People are using much better shoes, clothing. They're using much better training regimes. And that's what's leading to a lot of the improvement, is a better understanding of how to get the best out of the human body. But we are really not evolving fast enough to see a difference in the Olympics performance, because we've been around for millions of years, and it's taken millions of years to hone the human genetics to what it is. So we're not going to be seeing the evolution of humans fast enough to break records by genetic tweaks. But what we are seeing is the better use of our understanding of how we work as humans and how to get the best out of ourselves, so that we can optimize nutrition, we can optimize training, we can optimize approaches, including psychological approaches to these races and these events, to get the best out of ourselves. So I think at the moment there probably is a maximum, and we're sort of at it, and there will be very, very slowly perhaps a selection from the population of the odd person who's the odd genetic anomaly that is going to be an even faster runner. But we're very, very close to probably what is the theoretical limit.
If we're talking about collective evolution, if more of us are living more and more sedentary lifestyles, and everything's mechanization and everything's done by AI and robots, collectively there is not that evolutionary split or growth for us to, or need for us to go faster or throw further.
Well, people often say, are we still evolving? The answer is yes, of course. I mean, every time you have a baby, you're passing on 50 to 100 new genetic changes that are not in your body, but they're in your offspring, and that's how we evolve. So we're continuously updating our DNA and changing, but we're changing in response to selective pressure from our environment. The insight that Charles Darwin had was that things evolve, things are selected by the pressure applied to them by their environment. Historically, that pressure was, where's my next meal coming from? If you evolve like our ancestors did on the African continent, over hundreds of thousands of years, the pressure was on not being eaten by something nasty, not being eaten by your colleagues, and where do you get enough food and drink to keep yourself and your family alive? And we selected for people that were really good at surviving in really harsh conditions. Now we have changed those threats. Now the threat comes from the nearest supermarket, because the threat to us is eating too much. The obesity crisis affects half the world's population. So actually, we're in a race now to select for genes that mean we can live in the environment we've created and not be deleterious to our health. And so actually, evolution is continuously moulding us and fashioning us, but the pressures have changed. That's all.
It satisfies an answer or a question periodically. But the question is the naked scientist naked, or is he in a trench coat?
No, of course. Of course. It's very hot here, as I said. It's nearly sauna temperatures in this studio. So naturally, it goes without saying, it's good to do it au naturel.
Thank goodness we're on radio. But Dr. Chris Smith, the naked scientist, he's back with us next week. Thank you so much.
It's a pleasure. Thanks,
good
Lester.
weekend,
Bye-bye.
Chris.